Okay, so we got a rough idea of how SSS star works. So let us now move on to looking at the algorithm itself, and this algorithm that we are looking at is an iterative version, and it works in 3 phases, as we will see. Uh, in the initial phase, you start by adding the root node to the priority queue. It is a best first version, so it will maintain a priority queue, and we will continue till the root is solved, and it is at the head of the priority queue. At that point, when the root is solved and at the head, we will terminate. So every node in our priority queue will have 2 possible values. So it will be either solved or it will be live essentially. So we start off by saying that root is a live node, we still need to work on it. But at some point when root will become solved, then we will be able to terminate, in the sense that we know the value, minimax value of the root essentially. The minimax value is stored as a third parameter here. We start off by saying infinity, or which is equivalent to saying plus large, that plus large is the limit for max essentially. The plus large corresponds to win, if you remember, that it can go as high as a win essentially. And then of course we will see if that is really the case. So every node will be represented as a triple. What is a triple? It contains 3 values. One is n, which is the node itself. Then it has a status, which we have seen will be either live or it will be solved. And the third is its value, which we will call as the h value essentially. So at the point when the root is labeled solved and it is the best node, which means it is at the head of the priority queue, we will return terminate the algorithm and return the value h. But we started off by saying that we will add root as live and infinity to, or plus large to, the priority queue. So we take out one node at a time. So initially what happens, we put this root node with live and plus large or infinity into the priority queue, and we extract it, right. So we pop the element at from the open, which is the priority queue. If the status of that node is live, then we do the following. Now this we are entering the second part. We will look at this again in a bit more detail. In the forward phase, we add live nodes till we reach the horizon essentially. And what is happening here? If the node that you have popped from the queue is a live node, then we check, is it a terminal node? If it is a terminal node, then make it solved, because we are not going to look beyond the horizon, and its value will become the lower of the value that we pass to it and the evaluation function. So remember that the value we are passing to it is infinity, and therefore obviously its value will now come down to the value returned by the evaluation function. So in this way we reach the terminal nodes. If it is not a terminal node, that means if it is an internal node, we will look at this in more detail, is that if it is a max node, then for each child C of that node, we add that child to the priority queue. So remember, this is a process of computing the clusters. At max level, choose all children essentially, and of course give the same upper bound as that was passed to it essentially. But at the min level, you just choose one child, and without loss of generality, we will choose the first child of n, and all these nodes will be live nodes essentially. So we will keep adding these live nodes, which means we will keep going down the tree and building the clusters. So as long as the node we are popping is live, we will keep going down the tree and adding more live nodes till the point where we reach the horizon or the terminal nodes. At that point, we evaluate those nodes and put their value into those nodes essentially. So after a certain point, all the nodes on the horizon would have been accounted for in the clusters, and all of them would be solved because we would have applied the evaluation function to them. So, the next time that you pop a node, so remember that we are still popping a node, the next time we do that it will be a solved node essentially. By now all the values have come down from infinity to the particular specific evaluation functions. So, the best node will be at the head of the queue and it will be a solved node essentially. Then what do we do? If n is a solved node, we identify its parent p, and if n is a max node and n is the last child, that means all the siblings have been evaluated, then we add the parent as a solved node to open essentially. If n is not the last child and it is a max node, then we add the next child of p to open. This corresponds to the recursive call that I was talking about, where once you have solved the max node, you recursively solve its sibling essentially. So, this is taken care of here, and if n is a min node, then we simply label its parent as solved, because n is not only it is a min node, it is a solved node and it is at the head of the queue. So, it is solved. So, all its siblings would be only lower than what this value has, and therefore, its parent can be labeled as solved essentially, and it is added as solved to open, and also we remove all successors of this parent from open again. So, we will see this in more detail. So, there are two phases. In the forward phases, we construct the clusters, add live nodes till we reach the horizon, only evaluate it at the horizon. In the backward phase, when we are looking at solved nodes, we apply the backup rule and we keep refining these things. So, this is just the same algorithm in three separate parts. So, the initial stage is what, add the root node as a live node with a value infinity, this thing, and at in every cycle of this loop, we are going to pop the node from the open, which is a priority queue, which means the node with the highest h value will come out essentially. If the node which comes out is the root, so remember this n is the one that is being popped. If n is equal to is the root and it is solved, then we will terminate the algorithm and return the value of h. So, that is the termination criteria. The second phase, which is the forward phase, again we have popped this thing. Remember, we are in this loop, in every cycle we are doing this. In the forward phase, we will pop a live node essentially. So, we are checking here if the status is live, and for terminal nodes, invoke eval n and choose the minimum of the bound. What is the bound? The bound is h, that is coming from the top, and eval n is the value that we get from the evaluation function. Remember that this bound h was infinity to start with essentially. So, obviously, if a leaf node has a value lower than infinity, then that should be its value, and that is what we are doing by saying that choose the minimum of these two values. That is when you reach the terminal nodes essentially, you reach the horizon. If you are not in the horizon, then you are still constructing the clusters, and the strategy for constructing the clusters was that all children of max and one child of min. So, if n is a max node, then for each child c you add c to open essentially. Otherwise, n is a min node, just add the first child to open essentially. In this manner, we will keep going down towards the horizon, and at the horizon we will also replace them by solved nodes with the evaluation function value. So, this is a forward phase in which clusters are formed. And finally, the backward phase, which starts from line 15 of our algorithm. Again, we have popped this node n, and if the status of this n is solved, and that will be the case. So, remember that in the forward phase we will go down to the horizon, then we will evaluate every node on the horizon, replace the value with the evaluation function value and call them as solved nodes. So, at the end of the first forward phase, we have a set of solved nodes, each with their evaluation function value essentially, but they are organized in a priority queue. So, the highest value node comes out first essentially. Now, the node that we we extract is a solved node at that stage from the horizon, and we identify its parent as P, and then we say if that n is a max node and n is the last child essentially. What does this mean? That you let us say evaluated this as 13, then its sibling you evaluated it as 15, then its sibling you evaluated as let us say 10, and let me introduce a negative number here as well, just to remind you of the fact that there could be negative numbers. So, I have a habit of writing only positive numbers in these examples. So, what is happening? This is a parent P, and these are all max nodes, okay, and these are all evaluated. So, let me use a double line to represent the fact that they are evaluated, they are solved essentially, that we know their value exactly essentially, which is true at the horizon. So, we are popping these nodes. Okay. So, what happens? Let us say we pop this one first, 13. Okay, the other nodes are not yet there essentially. If max so look at this second case here. So, it is a max node, but it is not the last child. So, this is a max node, let us say 13 that we pop, but it is not the last child of its parent. So, what do? We add the next child of that parent as a live node. That means, we add this as a live node essentially. We will add this as a live node, then if we pop it again, it will be a live node on the horizon, and it will become a solved node which is 15. So, in that manner we will pop this, then we will add this and so on, and in the end we will add one more node, and let us say that is the one that is popped out. Once that happens, it is this case, it is the last child. If the node that we have popped, remember that we are always popping the node with the highest H value, it is a max node. So, this test is applied here, and it is a last node which is also a test which is applied here, in which case what we say is that if minus 10 is the best that we are looking at, then we add the parent which is the min parent, and we say it is solved, and its value is in this example minus 10 essentially, and we add it to open essentially. So, when you are looking at solved nodes, there are two cases. One is when it is a max node, and the other is when it is a min node essentially. When it is a max node, it depends on whether it is a last node of its parent or not the last node of its parent. If it is the last node of its parent, then we say we have solved the parent. If it is not the last node of its parent, then we say okay, solve this sibling of that max node, and then we will decide what is happening. That is one case. The other case is if n is a min node essentially. So, just imagine that let us say this has got its value minus 10 or something like that, okay, and let us say this is the one that is popped next. So, we have a min node whose value is minus 10, and it is a solved node, and we have popped it from the queue essentially. Now, the key thing to remember is that when we have popped it from the queue, from the priority queue, it means it is a value node with the highest value, because the priority queue has always the best node at its head essentially. So, if we have popped this node from the priority queue and it is a solved node, it is a min node and it is a solved node. Remember, these two properties are there, it is a min node and it is a solved node, and we are popping it from the queue essentially. So, min because it is a circle in my notation, and solved because it has got a double circle essentially. So, we pop it. Now, what happens? Supposing there were other min children of this node, other min siblings of this node, those siblings would have a value of less than minus 10, because minus 10 is at the head of the priority queue, and there is a max parent sitting here. Okay. This max parent says, okay, I am getting the best value I can get from its min children is minus 10. Why do I again repeat this? The best value, because it is at the head of the priority queue and we have extracted the node from the head of the priority queue. If the value of its best child is minus 10, then the other children need not be looked at all essentially. And then we can say add this as a solved node. So, add P the parent as solved with the same value, which is minus 10 in this example, to open. This is the backward phase. Remember that we are propagating these values up there essentially. What is more, you remove all successors of P from open. What are the successors? These 3 nodes that we have run. We do not want them anymore. Their values are known to be less than minus 10, because minus 10 was at the head of the priority queue. So, we can just remove them and we can say its max parent is solved essentially. So, in either case, if you are looking at a min solved node, it is simpler. You can simply say its max parent can be labeled as solved, because that is the best value that we could have got. If it is a max node that you are looking at the solve as a solved node, there are 2 cases. Is it the last node? If it is the last node, then there are no more children and its parent can be labeled as solved. If it is not the last node, then we will add its siblings to the priority queue and refine them, and this is what we call as a recursive call. We call it a recursive call, but in practice in this iterative version this is how it happens. Because remember that when we added the sibling, then we created clusters and everything all that was happening. So, let us look at this process in more in a little bit detail. Oops. So, anyway, what I have written here is that if max node is not the last child, then add sibling, else for both max and min you add the parent as solved, which is what I was explaining just now essentially. Now, just a programming note, if you are implementing this SSS star algorithm, we keep saying if it is a max node do this, if it is a min node do that. How do we identify that essentially? So, one way that you could do that is by adding another parameter to the representative. Instead of making it a 3 tuple, or instead of making it as a triple which had root and status and h, now you add this 4th parameter called player essentially. So, it is a node, the name of the node, which is n in this case, and whether it is a max node or a min node, that additional information you can add. So, that this is the kind of check you can do, that instead of saying it is a max node, you can say if player is equal to max or something like that, or if player is equal to min. It is just a programming note. So, let us again go through this process. First, we initially add the root node as a live node with a value of plus large to open essentially. So, our priority queue has only one node in it essentially. Then we follow the algorithm. What does the algorithm say? Pop this node from the priority queue. If it is a live node and if it is a max node and if it is not a terminal node, then add all its children. That is what happens in the next this thing. So, we pop the top element, which is the root element. So, this cross simply says that it is no longer there in the priority queue, and it is a max node and a live node. We add all its children as live nodes to the priority queue. So, these 3 nodes now have gone into the priority queue. All of them have a h value of plus large, because that is what we have started it. This plus large value will change only when we hit the horizon. When we hit the horizon, at that point we will call the evaluation function for a particular node, and then we will get its real value. But for the moment we are saying it has an upper bound of plus large. Then the same thing happens at the next level. The next 3 elements we popped are live nodes, and these are min nodes with a value of plus large. For each of these min nodes, we add one child, which is a live child with a value of plus large. At the horizon, things change, because the test of if it is a terminal node, then and it is a live node, then replace it with its evaluation function value, or at least a minimum of h n n value. And that is what happens in this example here. We have in this slightly bigger game tree, we have 6 initial clusters essentially. And if you look at the thick arrows, you will see that those arrows represent how those clusters were formed. At the max level, we chose all children. At the min level, we chose one child. In particular, we chose the leftmost child. So, they all the nodes that you see, these 6 nodes will go into the priority queue. Only these 6 nodes. The rest of the tree is just for our reference. These 6 nodes will go into the priority queue. These 6 nodes are terminal nodes and they are live nodes.